No. Oh shit.
It's recording.
That out. Okay. So let me share my screen. Okay. You guys see my screen and everything?
Yeah.
Okay. So the first thing I thought we'd go over was just like the basic periodic table. So like some periodic trends and stuff like that. And then I thought I'd go over the Pka table that he made us memorize last semester. So what one do you guys want to go over first? Do you guys want to go over the Pka table or just trends?
Doesn't matter, pick one.
Okay. So we'll go over periodic trends first. So up here is the number of electrons that surround the actual atom itself. I think you guys all know that. And then down here in blue is going to be the number of connections it typically makes. So not connections, but bonds it typically makes. And then if you guys remember, anything after carbon is always in the octet. And as you go down this way, the atom becomes larger, and as you go to the right, the atom becomes more electronegative. And that plays a role in stability. That makes sense to everybody? You guys remember all that?
Yeah.
Okay, and then remember, these are ionic because they're metals. So if they're next to like, say you have something like this. Since this is positive, in order for the molecule to actually be neutral, the chlorine becomes negative, has a negative charge on it. And that's going to play a big role when it comes to SN1 and SN2 reactions, dealing with the halogens. Make sense?
Yes.
Okay. So now then I'll go over the Pka table real quick, and then I'll go over ARIO, and I have a couple problems relating to stability that we'll go over. And then we'll move on from there. So these are the Pka values, and the lower they get, the more stable it gets. That's a 16. 10, 9, 5, 3, 1, 0, -5, -7, -8, -9. And this is going to be CH4 or an sp3 carbon. I'm not going to write carbon because I don't have enough room. So for 45, it's going to be an sp2 carbon. You guys remember hybridization, sp1, sp2?
What? Can you say that again?
Do you guys remember hybridization? So like for the Pka value of 50, it's a CH4, which is an sp3 carbon.
Yeah.
For 45, it's going to be an sp2 carbon, which means that it's going to be a carbon with a double bond and then two regular bonds. Because remember, for the hybridization, you count either the lone pair as one, that'd be S, and another bond would be P, and then 2, and you guys remember that, right? Or do you want me to go over that?
I think I'm good. Mimi, are you good?
Sorry, I'm just trying to catch up. It's been a little fast.
Oh, sorry. And then for Pka value of 4, you got ammonia, NH3. And for 35, you got hydrogen bonded to hydrogen. For 25, you got sp1 carbon, which looks like this. So here's hybridization. See how there's only one overall actual big bond with an alkyne bond, triple bond? That'd be sp because it only has that one. So you'd only count it once. So it'd just be sp. And then it's also attached to hydrogen. There's a bond to hydrogen. So the carbon is sp hybridized because there's 1-2 bonds. So it would be sp. That makes sense?
Yeah.
Okay. And then for 19 pK value, you got this, and for this, 18 for butanol, and then for 16, that's going to be your alcohols and also water. So then CH3OH, and then you also have CH3, CH2OH. So methanol, ethanol, water, stuff like that's going to be pK value 16. And then for 10, you have C6H5OH, which if you draw that out, it's a benzene ring with an OH attached to it. That make sense?
Yes.
Okay. Now then for 9, you either have this or you have NH4 positive, and then if you actually drew its conjugate base and acid, it'd be NH3 ammonia. And then for 5, that. Then for 3, you have HF. Then for 1, F's supposed to be capitalized, my bad. Then for 1, 0, H3O positive, -5, you have H2SO4, -7, you're going to have HCl, HBr, and then your strongest acid is going to be HI, and that's your most stable. And then when we get into leaving group abilities, there's actually, if you remember, these are the best leaving groups, and as it goes in this direction, it's the better leaving group. So if you had iodine on the molecule, that ionize the fastest when compared to hydrochloric acid, hydrobromic acid, and sulfuric acid. But that's like the basics for pKa and the periodic trends that we have to deal with in order to solve these next couple practice problems. Does that make sense to everyone?
Yes.
So next thing up is going to be ARIO, and all ARIO is if you remember the first, so this is how you determine stability if it's not on this pKa table. You guys remember that, how you would utilize ARIO?
Yeah. I remember
one,
that R is
first,
resonance, the first one is and I is induction, and then the O is orbital. I don't remember what A was.
yeah, 1 second, I gotta take a picture of the actual link for somebody. How do I do this? Okay, so 1 is, as you said, atom, 2 is resonance, 3 is induction, 4 is going to be your orbitals. So when you're dealing with the atom itself, that's why I kind of taught you that periodic trends. Okay, so as you go this way on the periodic table in the same column, it becomes more stable. So oxygen is more stable than nitrogen. Fluorine is more stable than oxygen because of its electronegativity. And as you go down in the same column, it is also more stable, because the atom becomes larger and it holds the electrons more closely to the nucleus, meaning that it's a more stable molecule overall. Does that make sense?
Yes, sir.
Don't call me sir. I'm not Dr.Paull. Resonance is the next thing, and basically all resonance deals with when it comes to ARIO is the more resonance that the molecule possesses, the more stable it is. Does that make sense?
Yes.
Okay. Next thing is induction, and induction actually has 3 roles of its own. So the first role is when you're dealing with induction. 1 second. The first role is going to be the actual distance away from the inductive atoms. Second is the number of the inductive atoms on the molecule, and then 3 is the electronegativity. So of course, fluorine is going to be the most electronegative halogen out of the 4 halogens that are going to be present for inductive properties. And I'll show you on the next practice problem how to do all of this. So if this doesn't make sense, you'll get it once we do the practice problem. And then the last one is orbitals, and I doubt you're ever going to see this in orgo 2, but just know that sp1 is more stable than sp2, which is more stable than sp3. Make sense?
Yeah.
So this is the practice problem, and all I want to do is determine which hydrogen is the most acidic, or as pertaining to stability, the more acidic it is, the more stable the molecule, the hydrogen actually is. So how do you guys want to do this? Do you guys want to try and solve it yourself, or you just want me to walk you through it?
Mimi?
I'm just in the middle of drawing it, so I can try to do it on my own first, and then afterwards we can go over it.
Okay. So do you want me to start like explaining it, or do you just want to do it on your own straight up?
Honestly, can you explain it so we can get this going?
Yeah. Okay. So utilizing Orgo, the first thing you want to look for is, of course, once the hydrogen leaves, it would then add the electrons onto the atom it's currently present on. So this would actually become negative, and then this could resonate onto here, and then this negative charge could resonate onto here. So you then have two oxygens with a negative charge. So what's that mean? If you have two oxygens with a negative charge, that means since there's two oxygens carrying the negative charge, it's going to be more acidic than this hydrogen, because if the negative charge comes here, this could then resonate here, this could resonate here, this could then resonate here, and this could resonate here. I'll do each one color-coded, actually, to make it. And then that means that actually only one oxygen carries the negative charge. So since only one oxygen carries a negative charge, the hydrogen that caused two oxygens to carry the negative charge is going to be more acidic than the hydrogen that only have allowed one oxygen to carry the negative charge. So this is for the blue hydrogen. And now then we know that these aren't going to be the most acidic whatsoever, because the negative charge can't resonate onto the oxygen from any of these, if that makes sense. You guys can see that, right?
Yeah.
Okay. So now then we'll test the last one right here, is then this one. I don't like brown, that isn't going to show up very well. So this is going to be your last hydrogen to check. So I'll raise this hydrogen, and then just put the negative charge here. It can resonate here. This can then resonate here, and then this can resonate onto the oxygen. So there's still, once again, two oxygens carrying the negative charge, but which one actually possesses more resonance compared to the top and the bottom oxygen? The purple or the red? Which one contained more resonance overall?
Would it be the purple one?
It would be the purple one, because the resonance is traveling a longer distance. So actually, a carbon would actually possess an electric charge or a negative charge in one of these resonance forms. I just didn't draw each resonance step out because that take really long. So if you actually label this for acidity, this hydrogen right here would be 1. This would be 2. This would be 3. This would be 4, because it's closer to oxygen, which means it has more inductive oh wait, my bad. That would not be 4. I forgot about this oxygen down here. So this would be 4, this would be 5, and this would be 6. Does that make sense, utilizing Orgo?
Yeah.
Okay, the next one's pretty simple, so you guys can understand it a little better. So for this one, there's not much resonance here, so you should be able to just utilize Orgo pretty efficiently. So we know that with this hydrogen right here, there's not going to be able to be any resonance, because no matter where you go, you can't resonate the bond onto one of either of these oxygens. However, it has inductive properties due to the fluorines being attached to that carbon. So this has inductive properties. However, it's definitely not going to be one of the most acidic. because if we check this hydrogen right here, what can this hydrogen resonate with? And also, if you put stuff in the chat, I can't see, so I apologize. It can resonate with both of these oxygens. So that means that because if you go this way, you can resonate that charge onto this oxygen. And then if you go this way, you can resonate that charge onto this oxygen. So that means the electric charge or the negative charge is carried on two oxygen, which is very good for the atom, the A in orgo. Now then, does that make sense for that one? Purple
Yeah.
hydrogen. Okay, now then for this one, if you actually did the resonance here, how many oxygen would carry the negative charge after resonance?
Wouldn't it be just one?
Yep. So that means that this middle hydrogen is slightly, well, not, I can't tell you exactly pK value because actually I can, it'd be 19 because of that Pka table. So this would be a pK of 19. And this one I can't tell you because we have to use RO to figure it out. But this means that this hydrogen right here is more acidic than this hydrogen. And now then this hydrogen right here, it can resonate with only one. But why is this hydrogen slightly more acidic than this hydrogen? What does it possess?
Is it because it's closer to the F3C?
Yep, so it has inductive properties on top of being the negative charge being held on that oxygen. So this would be 1, this would be 2, and this would be 3 because we do atom first. And then why is this hydrogen last even though it's close to induction and the inductive atoms?
Isn't it because it's furthest away from the oxygen?
Well, no, that's not why. It's just because it has no resonance and the negative charge wouldn't be held onto either of the oxygen atoms. Even though it has inductive properties, the atom outweighs inductive effects when it comes to stability. So this would be 4. Make sense?
Yeah, makes sense.
Okay, so out of these ones, which one would be the most stable, which would be the least stable, and which would be in the middle? So you always look for the hydrogens, and for this one, you have oxygen compared to nitrogen, which is more stable on the periodic table. Remember, the farther right you go in a column, the more stable it is due to it becoming more electronegative. And if you're on the same column, as you go down, it becomes more stable due to the atom being of larger size. So the electrons are held more closely to the nucleus. So out of these, is oxygen more stable or nitrogen more stable? Oxygen is more stable because it's further to the right on the periodic table. So we know that these two are going to be more stable than these two. Now, out of those two cyclohexanes or cyclohexanols, which one's going to be more stable, the benzene ring or the one without the benzene ring?
I would say the benzene ring, but is it because you can do resonance?
Yes. So this would be 1. This would be 2. Now out of these, same thing applies. 3, 4 for stability. Does that make sense for everybody?
Yeah, that makes sense.
So do you guys want to go over IUPAC rules real quick, or everyone good with those? Or just want to jump into the actual 3 practice problems? Oh, 4. My bad. I didn't know I had 4. You guys remember the rules for IUPAC?
Do you want to go over it?
Yeah. So
Thank you.
meth, eth, prop, bute, pent, hex, hep, oct, non, dec, oh, dec, undec. I've got awful handwriting, so I apologize. Undec, dodec, and tridec are going to be your prefixes when dealing with that. So this is when you have 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and so on, up to 13. You're never going to see a carbon chain longer than 13. Most likely, I mean, if you do, I'm sure he's going to give you the name of it. But for naming reasons, 13 is probably what you need to know up to. And then after you know what you want to do is you want to pick the longest parent chain first. Actually, I think the most efficient way is to just kind of show this on a practice problem, because it's a little hard to explain IUPAC rules without doing practice problem. So what you want to do first is you want to find the longest parent chain. So by doing that, you want to count the carbons. So 1, 2, 3, 4, 5, 5 there. 1, 2, 3, 4, 5, 6. So we know that the ones with the red dots is going to be our parent chain. So once you figure out your parent chain, you then want to figure out which substituent would be closest to the starting point. So you want to have the most simplest substituents. And what I mean by that is you want to have the maximize your number of substituents, but you also want to make sure that they're the simplest. And you also want to make sure they're closest to the starting point of the parent chain. So you wouldn't go this direction, because that would mean that your first substituent is at 1, 2, 3, 4. And if you went this direction, it'd be at 2. So you'd want to start the direction that would put the methyl on 2. Does that make sense for that?
Yeah.
So then this would be, if I labeled this 1, 2, 3, 4, 5, 6. So then how I like to do it is this is going to be hexane. I like to draw each thing, write each thing out, and then put it together at the end. Hexane, and then there'd be a 2 methyl. If it's a substituent, you add O at the end of it. And then this would be 3 ethyl. And then for IUPAC rules, when you organize it, it goes in alphabetical order. So E comes before M. So it would be 3 ethyl, 2 methyl, hexane. That makes sense?
Yes, thank you.
Okay. So the next one is going to be, if it's a ring structure, it's going to be cyclo. And for cyclo, it follows the same rules. You want the closest and the most number of simplest substituents. So you would do, you would do 1, 2, 3, 4, 5. Now then, what's special about this molecule is these actually have their own. So there's a few things that actually have their own specific name. I'll write those out real quick. That's isopropyl. That's tert-butyl. That's sec-butyl. That's isobutyl. Neopentyl. Isopentyl. So these are the only substituents that actually have specific names that don't actually utilize the methyl ethyl and all that. So since this molecule actually possesses 2 of those specific substituents that have unique names. Oh, sorry. I'm also recording this, so if that helps. Am I good?
Yeah, I'm good.
You're welcome. So if I erase all this, and then we'll name this one. So since I already have it numbered, of course, the cyclopentane is going to be your longest parent chain. So you would do 1 would be isopropyl. Then you would have 3 isopropyl, and then this would of course be cyclopentane. So if you put this all together, remember if you have two of the same substituents or three, it goes di, tri. You guys remember all that? So this would be 1, 3, tri, iso, propyl, cyclo, pentane. Does that make sense? Try di, my bad, not try, di. Because there's only two. Because if there's more than one repeating substituent, you have to label it. So it'd be 1,3-diisopropyl cyclopentane. Does that example make sense to everyone?
Yeah.
Sorry if I'm going fast, guys. I don't want to keep you like too long. Everyone's busy. So for this one, this is an alkene. So the only thing that's different about alkenes is you put "ene" in the name of it, and it follows the same rule. However, the alkene, which is the double bond, is going to take priority over other substituents. So this would be 1 because it's closest, 2, 3, 4, 5, 6, 7. So this would be heptane. However, that's not going to be the name when we're done. And then there's a 1 ene, there's a 3 ene, there's a 5 ene, and then if you put this all together, that would then be 1, 3, 5 hepta tri ene. And then I'm not going to go over E and Z nomenclature because I doubt you're going to need it for organic chemistry too. But if you remember, this would actually be for the alkene between 1, or the alkene that starts at 3 and ends at 4 would actually be E or Z nomenclature, because the two functional groups, which are these, the two largest functional groups, are on the same side of each other. So that makes it Z. And if they're on opposite sides of each other, it's E. But I don't think you really need to know that. I doubt he's going to ask you. So do you guys want to do this last one, or do you guys want to move on? Do you guys catch the drift of all this?
I'm good.
Okay, yeah, I'm good.
Good to move on to the next subject. Okay. So this is just Newman projections. Is the next thing I wrote for the review. And basically Newman projections just allow you to view a molecule in a different realm. So it allows you to visualize it differently and allows you to make bond rotations more efficiently and be able to tell the stability of the molecules in its stereochemistry. So do you guys remember how to do Newman projections?
Actually, can you go over that, please?
Okay. So we'll go over that. So if you're looking at it from the right side, you have ethyl on a wedge, and you have hydrogen on a dash, and you have methyl down. And then this right here is your backbone. So when you draw it, the dot acts as your backbone. It's that chain. If you're looking from it from the right side or the left side, going to the right. Wedge is right. Well, first off, put the methyl down. Then wedge means towards the right. So ethyl. Then hydrogen, which is on a dash, would go to the left. And then you draw a circle in the back. And then you would draw a methyl up, and you have to realize that there's a hydrogen on a wedge here and a hydrogen on a dash. So that means you would have hydrogen, hydrogen, methyl. And then if you rotate this is how then you determine stability. So all you want to do is draw the exact same type of structure. However, you want to choose either the back or the front to move, to rotate, not move, rotate. And I like to keep the back the same. So methyl, hydrogen, hydrogen. I like to rotate the front. So then you just move each one over one. So ethyl would come here. Methyl would end up here. and then hydrogen would end up here. Let's do this again, one more. The hydrogen would end up here. Ethyl end up here. Methyl would end up here. Methyl, hydrogen, hydrogen. So now then this allows us to determine the stability, which rotation is the most stable. And to determine that, you can utilize this trusty little chart, which so as you go to the left on this chart, it becomes less stable because the functional group becomes larger. It has more interactions when it's anti or gauche. So I know that's probably confusing, but what that means is for this one, you have methyl interacting with ethyl. You ignore hydrogens because hydrogens carry very little influence on stability. So for this one, you have methyl interacting with ethyl. For this one, you have methyl interacting with methyl. For this one, you have ethyl interacting with methyl. And you have methyl interacting with methyl. So out of those three, which one would be the most stable? Well, we know for sure this one's the least stable because you have ethyl interacting with methyl and you have methyl interacting with methyl. The middle one, you have methyl interacting with methyl, and then for the far left one, you have methyl interacting with ethyl. So ethyl is R, because R just represents a carbon chain. So this is actually ethyl. So methyl and methyl is more stable than ethyl and methyl. So this would be your most stable, second most stable, and third most stable. Does that kind of make sense?
Yeah.
I know it's confusing. I apologize. But it just, all Newman projections allow you to do is determine stability of the rotations and which molecule would be the most. They're really helpful when it comes to mechanisms, actually, which you'll see in the next couple slides. So for the next one, the only thing that changes when you're going from right, when you're visualizing this, so this is a picture of an eye actually, so that just means I'm looking at it from the right to the left, is that now a wedge goes to the left and a dash goes to the right. So same thing though. When you draw this, you have, oh man. You have OH up. However, methyl is not going to be going to the right anymore. But well, I guess it is because there's two methyls. So this would be methyl and this would be methyl. But instead, I'm going to make this fluorine just so you guys see what I mean by that real quick. So instead of it being on the right, it would actually be and then you would have methyl. Or no, you'd have hydrogen. Then you would have methyl, and you would have OH down. Does that make sense? How it kind of flips if you go from the right to left instead of left to right?
Yeah, that makes sense.
Okay. Do you guys want to do the stability of this one, or are you guys good with just being able to visualize it? Because if not, I'll go on to the next subject. Because it's the same thing. You literally just rotate it again, and you determine which one, by utilizing that chart, you determine which interactions are going to be the most stable. So you want to do that or just move on?
Do you want to do that? Just if, you know, anybody's watching the video, they're like, oh, what does he mean?
Chlorine, OH, Then keep the backbone the same. Methyl. OH. No, my bad. Chlorine. OH. Methyl. You guys see how I'm doing this, right?
Yeah.
Methyl. So for this one, let me move these so that you guys can see them a little bit better. Okay, so here you have methyl interacting with chlorine. You have methyl interacting with OH, and you have OH interacting with OH. Here you have methyl interacting with chlorine, methyl interacting with OH, and you have OH interacting with OH. And then you have methyl interacting with OH, methyl interacting with chlorine, chlorine interacting with OH, and then you have methyl interacting with OH. So out of these ones are actually equal. And you see why? Because they literally have the same interactions with one another. So these would be tied for the most stable, and this one would be the second most stable. And that's because this one has the most interactions overall, and there's no real determining interaction between these two to tell which one's the most stable. Does that make sense?
Yeah, so there's no tiebreaker.
Yeah, so these ones you just have to label as most stable, and this one you'd label as second most stable. Make sense, everyone?
Yep.
Okay, sounds good. Okay, so Rns configuration. So Rns basically allows you to determine whether it's a Meso compound, an Enantiomer, or Diastereo Isomer, or if they're identical compounds. And all you really need to know for Rns is you need to know your atomic number chart. And now then for atomic numbers, it goes like this. And now this is 11, this is 19, this is 35, and this is 53. So now then with these numbers, after you memorize, you probably should memorize these for RNS, because atomic number allows you to prioritize the various substituents on a carbon or a chiral center, and then you would then either draw a counterclockwise circle around the molecules via the priorities, or you would draw a clockwise circle around them to determine RMS, which I'll show you in the next practice problem. So clockwise of priority is R, and then counterclockwise is S. But these atomic numbers are how you determine the priorities, and I'll show you the next practice problem how to actually do it. So so fluorine, I'll draw the chart out here actually. So 1, 5, 6, 7, 8, 9, 3, 13, 14, 15, 16, 17, 11, 19, 35, 53. So like I said, lowest priority gets 4, highest priority gets 1 when labeling the molecules. So you start at your chiral center, which has stereochemistry, and you look. So fluorine is going to be 1 because it has the highest atomic number. Then methyl gets beat by ethyl because this is a carbon and this is 2 carbons. So then the next one, so if it's the tiebreaker, you'd start at this one, look, it's carbon. You go over here, you'd see that this is also carbon. And you have to go over to the next molecule that is adjacent to it or bonded to it, which then for this methyl would be a hydrogen. And then for this ethyl right here would be another carbon right here. So carbon is a higher atomic number than hydrogen. So this is going to be 2, 3, and then 4. And then also what you need to know is that the lowest priority atom always has to be on a dash. So we don't have to do anything since this one's the lowest priority is already on a dash. And then you just draw a circle. And since that's clockwise, that's R. Does that make sense?
Yeah. I was gonna ask, didn't Paul say that it had to be like on a number too, like hydrogen had to be on some number?
Yeah, lowest priority has to be on 4.
Okay, cool.
That's why I have, if it's not, which the next one isn't, then you'll see what has to happen. So for the next one, chlorine is a higher atomic number than fluorine. So it'd be 1, 2. Methyl would be 3. This would be 4. So now, as you can see, we ran into the problem where the 4 is not on the dash. So in order to do that, all you do is, I just call it a switcheroo, but you just switch 4 with 3. So this actually becomes 4. This becomes 3. But if you do that, then you have to flip this 1 with this 2. So the fluorine actually becomes 1 and this becomes 2. And then you draw a circle and that's actually S. Does that make sense?
Yeah.
Okay, sounds good. So that's Rns configuration. The only reason you need to know that is to determine if a molecule is an enantiomer, diastereomer, meso compound, or if they're identical to one another. Oh, here it is. So diastereoisomers, enantiomers, and meso compounds. So a diastereoisomer, I'm just going to draw an example of a diastereoisomer real quick. I'm going to label it D so I don't have to actually write out that long ass name. But all that happens is, say you have 2 chiral centers. And then next one looks like this. Since only one of the chiral centers change, not both of them, it's a diastereoisomer. If it was an enantiomer, I'll label this E. And the reason is because if you flip it, I'm not actually going to show you if it's R or S, but one of these is R, or both of them are R. They're either R or S. And if you actually figured it out, you'd be able to see that the R would, only an R would turn to S, and this one would either remain S or R. So like, I don't know how to explain that better. I'm sorry. So like, say this starts as R and R. I don't know if that's actually true because I didn't do the work. This would then, for a diastereoisomer, only one of them would change. So this would actually turn into S, and then this would remain R. Does that make sense?
Yeah, I think so.
And now, for enantiomers, say this is chlorine and this is bromine, and say we did the work and we determined that this is R and this is R. And then the enantiomer of this then would be, my bad, both change. So this would then be S and S. Does that make sense?
Yeah.
Yes.
Basically, enantiomers and diastereomers are only useful if you're in like forensics or stuff like that, because it allows you to tell if like the enantiomer of methamphetamine is actually Vicks Vapor Rub. So sometimes Vicks Vapor Rub can get confused as methamphetamine. But overall, if you're not going into forensics, it's kind of not useful. But you still got to know it, which makes no sense to me. So meso compounds is basically, there's an internal plane of symmetry. And it has R and S configuration. So this would be R and this would be S, the meso compound. All a meso compound is basically a compound that's identical to one another, but you don't know it. And they don't look identical, but they are identical. This has an internal plane of symmetry because there's bromine here, so they have the same constituents and all that. As Rns configuration. So if you're comparing this to something that looked like this, this would actually not be an enantiomer, even though both changed. It would be a meso compound because it has an internal plane of symmetry, and then this would actually turn into R still if you flipped it, and this would remain S. My bad. This would change to S and R. Does that make sense though? Because they're technically identical compounds. You'll see on the practice problem. That's all you need to know for that. Now, if you actually utilize this, it will allow you to determine whether each is meso, enantiomers, or diastereomers, or they're identical. So for this one, are these two compounds at the top, are they identical to one another, or are they meso, are they enantiomers, diastereomers, identical? What are they? Actually, guys, I screwed up this example because you can't even tell with these. I just realized I accidentally put a wrong substituent on there. Wait, my bad. 1 second. I have to flip this. This can't be hydrogen because these are actually, those wouldn't be related at all. This has to have a bromine on it. Okay, now you can figure it out. So this is going to be your number 1. This would be your number 2. This would be 3. So you're going to use RNS to tell if these are the same, identical, enantiomers, whatever they are. And this would be 4. So we don't have to do any flipperoo. We can just draw a circle. And we know that this is S because that's counterclockwise. Now then for this one, we know that this is our 1. We know that this is our 2, 3, 4. However, what do we have to do for this one?
Gotta do the switcheroo.
Yep. So this goes to, with this 4, this turns into 1. This becomes 3. This becomes 2. Now then if I go this way, that's R. So R and S. If you go from S to R, what does that mean? It'd be an enantiomer because the if you go to S to R, it's an enantiomer. I know it's kind of confusing. I'm sorry. Okay. So now then, this one is this an enantiomer, diastereomer, or meso compound? This one's kind of a trick question. You want to think it's an enantiomer because both the chiral centers go from wedges to dashes, but it's actually a meso compound because it has that internal plane of symmetry. This is R, this is S, this is R, this is S. So these are actually meso compounds, which means they're not enantiomers, they're actually identical compounds. They just look different from one another. So these are meso. Does that kind of make sense?
Yeah, I think so.
Okay. Okay, so chair confirmations. So here's like some of my stuff. Yeah. So all you want to, so all this chair confirmation allows you to do is tell the stability of a cyclohexane. It allows you to translate a cyclohexane into a chair and then rotate it and flip it and figure out what conformation is the most stable. So when you draw a chair conformation, it looks like this. And then up, or red is going to be my axial, and blue will be my equatorial. And they alternate. So it goes up, down, up, down, up, down. So those are my axial. And then I'll make my blue my equatorial. Okay. Okay. So axial is actually what lets you determine the stability. So if a substituent's in axial, that means it's going to have interactions with the other axial, which then determines the stability of the molecule, which we'll see in one of the practice problems. And a wedge points up and a dash points down. And this is down, this is up, 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 and then up, down. And that's the chair conformation. And then the next couple problems to see how to actually translate a cyclohexane into a chair, which I'll then show you how to utilize this. So for this one, to translate this into a chair, labeled. It doesn't matter how you number it, just as long as they're in the same position as so bromine will be at least 2 away from, we'll have 1 gap in between it, 2 away from OH, and it'll be 2 away from methyl. So we're not naming it, so you can number any way you want to go. So 1, 2, 3, 4, 5, 6. Then draw your chair. Okay. Now for our 1, I'm gonna say that this is my 1 right here. So 1, 2, 3, 4, 5, 6. Is OH up or down at 1?
Shouldn't it be up?
Yep. And now then there's nothing at 2. At 3, is methyl up or down? It'd be up.
Up.
And then for 4, nothing. 5, bromine.
Wouldn't it be down?
Yep.
Down.
Exactly. So now then, if we flip this, when you flip this, oh my gosh, my bad. I drew it the wrong way. It looks like this then. And all that happens is this one moves over here, but it has to keep remaining up. This one would go here, but it has to keep moving up or pointing up. And then this one would move over here, but that's pointing, still be pointing down. So if you do that, the OH then is, oh my bad. OH then gets translated instead of axial, it's now an equatorial. 3, 4, it's still up. So now then the methyl is also an equatorial. And now then this one is actually in axial now. So for this one, you have, like I said, you only look at the axials. So you would have methyl and interacting with OH. And then for this one, you would only have bromine. And if you remember that chart that I said, this is, you use the same chart as you did for the Newman projections. Bromine is going to be much more stable in axial than a methyl and an OH. And does that make sense? Because it's farther to the right on here, meaning it's actually a smaller functional group. So this one would actually be your more stable chair conformation when compared to this one. Does that make sense?
Yeah.
Because you have a methyl and you have an alcohol and OH and axial. Here you only have bromine and axial. So of course this one's going to be more stable than what I started. So for the next one, same concept. However, there's one unique thing about this. No matter how many things are in axial when compared to a terbutyl, it doesn't matter because terbutyl is what's called a locking group. So whenever it's an axial, that's the less stable chair conformation. It's like a weird rule. So if we draw this out, I'll draw these out real quick, just so you guys catch the drift. For the first one, I have, 1 second, my pen is unscrewed. I have terbutyl, then I have methyl down, And then I have iso. That's definitely really unstable. Those are all three in axial. And for this one, up, butyl, this would move over one. This would still be down. And then this would move over one, which would then be up. Yeah. So they all go from axial and they all turn into equatorial. Do you see that?
Yeah.
So either way, the terbutyl is a locking group. So whatever one terbutyl was in axial position would be the less stable one. So this is 100% your more stable conformation. That makes sense?
Yes.
So Sn1 versus Sn2. So we are now finally on, I think we only have like 5, 6 sides, 7 sides left. And it's just additions in Sn1, Sn2, E1, E2, stuff like that. And you kind of just utilize everything I went over previously to do this stuff. So first, I will draw the chart I use to determine whether it's Sn1 or Sn2. So Sn1 and Sn2. So Sn1 prefers a tertiary carbocation and Sn2 prefers a primary or methyl carbocation. I'm guessing you guys know what carbocations are, so I'm not, do you want me to go over that or is it cool?
Are you guys good with it?
Yeah, I'm good with it.
I'm good.
Okay, so now then for Sn1, Sn1, of course, likes sterics. That's why it prefers that tertiary carbocation. It likes protic solvents. It prefers a weak nucleophile. I'll go over nucleophilicity after going over this. Weak nucleophile. It undergoes carbocation rearrangement to make the most stable product. And it undergoes resonance in order to make the more stable product, because more resonance, more stability. And now then for Sn2, I'm gonna color code this blue just so you guys don't get confused. So this is, it prefers a strong, abbreviate nucleophile as nuke, nucleophile. It does a backside attack, which all that means is it inverts stereochemistry, which I'll show you in an example. It dislikes sterics. That's why it prefers to either occur on a primary or methyl. Polar aprotic. I'll go over the solvents also after this. Aprotic solvent, and then no rearrangement. So that makes sense? It'll make more sense once we actually practice problems, but those are like the rules of falls. And then if it's a secondary, that's what I'll go over next, of how you determine what occurred on a secondary carbocation. So does everyone understand this? So I can erase this and then go to the next step for secondary.
Yeah.
Okay, so if it's on secondary, then we look at the nucleophile. Nucleophile has some rules of itself, what makes a good nucleophile. So more basic, the molecule, the better the nucleophile. Nucleophiles usually have a negative charge on them. Electrophiles, of course, have a positive charge on them. Sterics, the less sterically encumbered it is, the better the nucleophile is. So for example, if you have something that looks like this compared to something that looks like this is going to be the better nucleophile because this has 3 carbons on it and this has hydrogens, which wouldn't actually interact with the nucleophilicity. So this would be a better nucleophile because it's less sterically encumbered with large functional groups such as carbons. And then after that, you look at the atom itself. And if you look at the periodic trends compared to this, as you go this way, you get a better nucleophile. So carbon's a better nucleophile than nitrogen, which is a better nucleophile than oxygen, which is a better nucleophile than fluorine. And then for the halogens, when you're looking at nucleophilicity, as you go down, it's actually a better nucleophile. So chlorine's a better nucleophile than bromine, which is a better nucleophile than iodine. Does that make sense?
Yeah.
So if it's a good nucleophile, it's going to go Sn2 because remember, like strong nucleophiles, and it's on secondary. And then also you have to keep in mind that HCl, HBr, HI, you know, I showed you all the ionic stuff, right? So like if Na is next to iodine, it actually means that iodine has a negative charge on it because sodium then has the positive charge, and to make it neutral, iodine would have to have that negative charge. Cl minus, oh my gosh, yeah. Cl minus, Br minus. The halogens are known as weak good nucleophiles, meaning even if they are on a secondary, even though they have that negative charge or they're an HCl, HBr, they can either go Sn1 or Sn2, and then you still have to look at the solvents, which is the final step you would utilize either way. So Protic would prefer to go Sn1, and then Aprotic would prefer to go Sn2. It'll make sense when I do examples, I promise. So now that I'll write out what a protic solvent is compared to an aprotic solvent. So protic solvents that Dr.Paull always would use were H2O, so anything alcohol, so ethanol, methanol, stuff like that, OH-based solvents. Acetic acid, and then NH3, also known as ammonia. And then for aprotic, you got DMSO, DMF, and then after that you have acetone, and then you would also have, which is CH3CN, which I forget the name for that actually, but those are your aprotic and protic. And then once again, this prefers Sn2, this prefers Sn1. So those are all the basics for Sn1 and that allow you to actually solve the Sn1, Sn2 problems. So I'm going to go on and now do the practice problems. So what's going to happen for this first problem? I'll draw it out. So like I said, Na is ionic. So this actually carries a negative charge on it. So this is a weak good nucleophile, which is iodine. This is a protic solvent. When the Br leaves, that would give us a secondary carbocation here. So we have a secondary carbocation, so we can't determine whether it's Sn1 or Sn2 unless we look at the actual solution in the nucleophile. So we have a weak good nucleophile and we have a protic solvent. So what would that prefer? It would prefer to go Sn1 because, like I said, if it's one of those weak good nucleophiles, protic, it's the solvent that determines what it goes. And what does Sn1 always like to do? What's the weird thing that's going to happen here before the iodine actually attacks the electrophile? So Sn1 actually then prefers to make the most stable product. So for the first one, I'll just draw out the actual mechanism so you guys understand. So the mechanism behind this would be bromine leaves. So I'm not going to draw step by step, but I'm going to show you what happens in real time. That would give you the secondary carbocation. Since this is Sn1, a hydride shift would occur. It would move over to this location here. Once that occurs, the carbocation then moves here because you now have a hydrogen here after the hydride shift, and that now makes the most stable carbocation, which Sn1 prefers. So then this iodine would come in and attack, and that would then give you your final product, which is that. And this would also be a racemic mixture because Sn1 makes racemic, meaning it makes the enantiomer also. Does that kind of make sense? It's a lot to process. I completely understand. Good to do the next one?
Yep.
Okay. So for the next one, all that's going to happen is iodine's going to leave. So that would then give you a secondary carbocation. Okay. So now that you have a secondary carbocation, you have HBr. And what's the weird thing I told you about HBr and the halogens? They can either go SN1 or SN2 on a secondary carbocation. So now then we once again have to look at DMF because that's our solvent. And what kind of a solvent is DMF?
Aprotic.
Yep. So this is aprotic. And what does aprotic favor?
SN2.
Exactly. So it wouldn't form the most stable carbocation. It would actually just attack. But the only thing that's weird about this, even though iodine was on a wedge, since it's SN2, Br is going to end up on a dash because it does that backside attack. So your overall product here would then be, oh, I didn't code that properly, but you catch the drift. Does that make sense? Oh, that's Br, my bad, not I. Does that make sense to everyone?
Yep.
So NaCN and H2O. I have a couple of these, and then we go into addition reactions, and then we are done. So this is T, D, and H. Well, H, of course, is the hydrogen. That's deuterium, which is just a special hydrogen, and then T is just another special hydrogen, just to show you stereochemistry. That's basically why we use them. For this one, what's going to happen? You have NaCN. So once again, it's an ionic compound, so CN is going to carry that negative charge, which is actually a really good nucleophile, CN, because like I said, carbon's a really good nucleophile. And this is actually when the iodine ionizes, that would be a methyl carbocation, which is going to favor SN2. So this would be an SN2 reaction, meaning that the CN, you can completely ignore the solvent. I just threw that in there to try and throw you off. The CN would come in, and it actually doesn't flip to stereochemistry. So the D is still going to stay on a wedge, the hydrogen is still going to stay on a dash, and the T is going to still stay like that. All that happens is it attacks from the backside. So your overall product, it would push this D up, push this hydrogen up, T would remain there, and then your C N would attack from the back. Does that make sense to that one?
Yes.
Okay. So for the next one, same thing. Bromine's going to ionize off because that's, oh, I forgot to show you guys leaving groups. You guys good with leaving groups? So basically for leaving groups, just look at it this way: H2SO4, HCl, HBr, HI. As you go down, ignore the hydrogens attached on those. I just wrote them as strong acids. As you go down, it's a better leaving group, which is kind of helpful for these. Well, it is helpful, but that's when you're dealing with more than one thing ionizing, which I think I only have one problem dealing with that. So for this one, bromine ionizes off, which would then give you a secondary carbocation. Once again, this is ionic, so the chlorine's negative, has a negative charge on it. Protic solvent. Then what's going to happen here? 2, 4, 6. Hydride shift to make the more stable carbocation. Once that occurs, then the Cl, the carbocation would actually then end up here. And then Cl is going to attack here, and then you would get this. Everyone good? Take that as a yes. Okay, so the last one for SN1 and SN2. Out of these two, that's why I just went over leaving groups. Which one's the better leaving group? It's going to be iodine. So what's going to happen here is iodine's going to leave, bromine's not going to leave because iodine's the better leaving group. NaCN. This is an ionic compound. CN is going to come in. Oh, I forgot. This is aprotic. So it's going to favor SN2. It would come in, attack, and now draw your product here. And that would be your final molecule for that reaction. So SN1, SN2 aren't too bad. Everyone good with these?
Yeah.
Okay. So E2 versus SN2 and E1. This is the last elimination and SN2 things you need to know before we go into addition real quick. So when you're comparing between SN2 and E2, this is how I always do it. So so this is E2 versus SN2. So methyl, SN2 is only going to occur there. Tertiary carbocation, E2 is only going to occur there. For primary, unless it's NDA or this, it's going to favor SN2. Now, if it is NDA or tribute oxide, so yes, then it's going to go E2, and it's going to form the kinetic product, not the thermodynamic product, meaning that it's going to eliminate with the hydrogen that's in the less encumbered spot. So instead of following Zatzky's law and forming the most stable alkene, it's going to eliminate from the outside hydrogen. And because these are such large functional groups, that's the only way they can actually fit in and eliminate. And then if it's not either of those, of course, it's SN2. Now then, if it's on a secondary carbocation, these you look at the pKa, and if it's less than 9, yes, that's SN2. No, if the pKa is between 9 and 16, you look at the solvent, and then protic, aprotic, and then aprotic, of course, still favors SN2, and protic favors E2. So then you have to utilize that pKa chart that you probably should have memorized in order to know if it's between 9 and 16. But most of the things in Dr.Paull's class that he gave us for eliminations, you're going to be dealing with alcohols because those are about the only things that are within the pKa range of 9 and 16. So like ethanol, methanol. There's no H on them though. They carry a negative charge for E2 and SN2. But those are really the only things you're going to be dealing with when it's eliminations for his class. And then you might see TBO minus to make the kinetic product in NDA. But I'll show you. And then is everyone good if I erase this real quick and show you E1 real quick?
Yeah, that's fine.
Sorry, I'm going fast, guys. I just don't want to keep everyone too long. Okay. So E1. So for E1, it's really rare. It only occurs if you have an aprotic solvent such as toluene and heat. Oh yeah, I forgot. Toluene is also a aprotic solvent. Dean Stark flask or concentrated H2SO4 sulfuric acid. And those are the only times an E1 occurs. So, and the thing with E2 is it has to eliminate anti-periplanar, meaning that if it's eliminated, the leaving group has to be opposite of the hydrogen it's eliminating with. So if the bromine that's being ionized is on a wedge, the hydrogen it's eliminating would have to be on a dash. And I'll show you that in one of the example problems. So for this one, you have toluene and heat. So what's that going to favor? SN1, E2, E1, SN2. It's going to favor E1 because heat and toluene is one of those rare instances where it favors E1. And E1 follows Zatzky's rule all the time, meaning that it is always going to form the most stable alkene. So what's going to happen here is bromine would leave, give you carbocation here. However, since this is E1, it always forms the most stable carbocation. So then you do a hydride shift here. Once you do the hydride shift here, it would form the carbocation there. And then what would happen is it would eliminate with this hydrogen, which would come here, go down, the toluene would come, grab that hydrogen, and it would form this. Does that make sense?
Yeah.
Now an ETO with a negative charge, and then H2O. So this is either, we know it's either going to be E2 or an SN2 because it's ETO, negative charge, and it's going to be on a secondary carbocation. So if we look at this, once bromine leaves secondary carbocation, we know it's E2 or SN2, like I just said. So now then we have to look at whether it is an E2 or whether it is an SN2. So ETO, secondary carbocation, H2O, protic solvent. Protic solvent is going to favor that E2. However, since the bromine was on a wedge and it is going to undergo an E2 elimination, what can't happen here? Does anyone know? It's like that one, it's that one weird thing why it can't do that. So it can eliminate with this hydrogen. Physically can't. It could eliminate with this hydrogen over here, but what's more likely to happen is it's going to follow Zatzi's rule, because you would get a minor product, which would be this would be a minor product. It would form a little bit of a kinetic product, which would be this. However, the overall product most likely wouldn't be this. What's going to happen is the molecule is going to rotate and it's going to eliminate like that. Because that would then, if you drew this out, if you rotate this bond slightly, not slightly actually, you have to rotate it fully. You would get that, and now it can undergo an E2 an elimination reaction because the bromine is opposite of the hydrogen. So you actually get two products technically for this. Like I said, you get this. And you get this, and this is your kinetic, and this is your thermo. But this is going to be your major product. Does that make sense?
Yeah, I think so.
So next one, I'm just going to do these kind of fast because I'm late. So MEO negative, yeah, negative charge, and DMF. It's going to be a secondary carbocation. We know once the iodine ionizes off, that leaves us with that secondary carbocation. So we know once again it's either going to be a SN2 or E2. It's on secondary DMF, it's going to be an E2 because DMF is that aprotic solvent. So all that's going to happen here is the iodine is going to ionize off. It's going to come in, attack, since it's an SN2, that stereochemistry is going to get inverted. So then you would get that. Pretty simple one, right?
Yeah.
Does that one make sense? Okay, so the next one. This one looks really hard, and it kind of is hard. But is this an E1, E2, SN2, SN1? It's going to be an E1 because H2SO4 concentrate is one of those rare exceptions where an E1 mechanism occurs. And the thing that I told you about the E1 mechanism is it always follows Zatzi's rule, meaning it's always going to form the most stable alkene no matter what happens. So you'd think that this bromine would eliminate and would form, pretend bromine's off. You think it would form this and just leave it like this. However, since it is that E1, these functional groups are actually going to be forced to rotate. And I'm just going to call this benzene. So it's a benzene ring. And this is a benzene ring. and they're going to be forced to rotate. Oh, my bad. This would get eliminated over. That'd be your overall product, actually, because it wants to, E1 always forms that most stable product, and the functional groups on opposite sides of one another, because they don't interact with one another when they're like this, makes the most stable alkene. And it can ignore, it doesn't have to do that opposite stuff that E2 has to do. E1 just always makes the most stable alkene. That makes sense?
Yeah.
I know it's kind of complicated. Once again, I'm sorry. So I think this is like the last things I have for you guys, just some various additions and various other interview mechanisms we learned last semester, and then we'll be done. I think there's like 10 to talk real quick, and there's only one practice problem pertaining to each. So these are addition reactions, and they're not hard at all. All that you have to know is send addition, anti-addition, Markovnikov's rule, and then you're golden with these. So for these, all that happens is if you see an alkene, it's most likely going to be an addition with an HCl, HBr, stuff like that. So what happens is your intermediate would look like this, because the hydrogen on right here always would form where there's more hydrogens available. It's where it's more substitutes. Since there's technically more hydrogens present over here, this hydrogen is going to form over here instead of over here. That's Markovnikov's rule. So the carbocation then would be formed here. You can also think of it how I never thought of it that way. I never really utilized Markovnikov's thinking. That's the real reason why. I just always thought of it as it goes, the carbocation forms for these where the more stable carbocation would be, and the hydrogen goes where the less stable carbocation would be. That's how I followed them for Markovnikov and anti-Markovnikov. So whatever way you want to think of them, think of them. And then what happens is once that's through, Cl attacks, and then it forms overall product. That kind of makes sense. So like, for example, the next one is the carbocation going to form here, or is it going to form here? Carbocation would form here technically, because that would then allow it to make a more stable carbocation with a hydride shift here. So when you actually do this, I'll draw out the entire mechanism for you guys real quick so you see how this works. That'd be your final product. Does that kind of make sense for that one? And then also, this would actually be OH, because I didn't realize if it's with additions, it's OH is going to take precedence because it actually means there's more H2O than HBr in the solution. So that's that one. And then for this one, all that's going to happen, that's on alkene, is you would get this H2SO4 adds an OH on for addition. Those kind of make sense? Are there any questions? Everyone good? Am I talking to myself?
No, you're not talking to yourself. I'm still here.
I'm here too.
So-
Just carrying up on writing.
HGOAC2, that's mercuronium. And the only thing that mercuronium does that's unique for addition reactions is instead of undergoing carbocations to form the most stable carbocation, it adds whatever it's going to add. And it adds whatever it's going to add right at the first carbocation it forms. And you know what it's going to add because it's the second thing after it. So say it's HGOAC2 with MEOH, it's going to add OMe with the negative charge, of course, onto it. So for example, I'll draw out this mechanism real quick. So carbocation is going to form here because there's more hydrogens here than here technically, when that's actually not the case. It's just more substituted here than there. And then what else? And then this come in, and instead of undergoing, because you'd think it'd want to undergo a carbocation rearrangement here, it doesn't actually do that since it is mercuronium. The O methyl just attacks right where the first carbocation is formed. So then that would give you your final product right away. So basically the same as the other additions, except when you see HGOAC2, it adds whatever's right next to it, and then it only undergoes where it attacks right where the first carbocation is formed. It doesn't undergo any carbocation rearrangements. So the next one is BCAH6, which I believe is called Hydroboronation or something. I forget the exact name of it, but all it does is it adds an OH and a hydrogen send to one another. So anytime you have a Sen addition, that means it's going to be stereospecific. So you really have to pay attention to stereochemistry because that's going to dictate how it's added Sen, and that means it won't have enantiomers. It'll only form one product. So for example, since we have a methyl attached on a wedge, the OH and the H is going to be added on a dash, because it has to avoid that functional group in order to be added properly. So the final product, he never taught us the mechanisms behind these because they were like really weird. I'm sure you guys remember that. You just kind of had to know how they added. But this is how it would add. And then the only thing that's weird is the OH, the hydrogen, it actually follows anti-Markovnikov, meaning that it's going to form the OH is going to attack less stable carbocation, which would actually be over here, and the hydrogen would attack here. So that's a Sen addition. So you see how they're both added via dashes, and by it being added via dash, of course, pushes that methyl into a wedge stereochemistry. And there'd be no enantiomer once again because of their BTH6 or hydroboronation or whatever it's called is very stereospecific. So anytime you see BTH6 and H2O2 and NaOH, this is the mechanism it undergoes. It adds an OH and an H send to one another, and it's stereospecific, and it follows anti-Markovnikov. So I'll actually write that down. This is anti-Markovnikov send addition of OH and H, and then stereo. And yeah, that's BTH6. Now then, same thing happens here. So your final product for this one, the OH, you'd want to think would go here, but that's actually not true. Once again, it follows anti-Markovnikov, meaning it's going to attack the less stable carbocation, and it would actually form, it's actually going to be put on a dash. H, and now since this one didn't have any starting stereochemistry, it would then also have an enantiomer. And as we went over earlier, all an enantiomer means is that hydrogen OH and then would be on a wedge instead of a dash. Yeah, that's hydroboronation, or I forget the exact name of it. Everyone good with these so far? I think we have like 5 left. Addition reactions, and then yeah, we're done.
Yeah, I think we're good.
So this is H2, and so no, this is I remember. Okay, this is hydroboronation actually. hydrogenation is what it's called for H2 and D2. And all it does is it adds 2 hydrogen Sen or 2 deuterium Sen. And once again, since the Sen addition, it is stereospecific. So for this one, all that would happen, honestly, since hydrogen doesn't really form chiral centers here, it would just remove the alkane. But in reality, what it's actually doing is, once again, it's adding 2 hydrogens Sen to one another like that. And then you would technically have an enantiomer, but technically there won't even be stereochemistry on this thing because chiral centers have to have 4 different substituents in order to have a stereocenter. So it honestly just looked like that for that one. Now in this one, since there is stereochemistry present and it is a Sen addition, we have to look at the stereochemistry. That's on a dash. So the deuterium has to be added Sen on wedges. So now then this would have stereochemistry and would actually be shown on the molecule. So you would actually end up with something that looked like this, and this would be your only product. So this would be knocked back, the methyl, and then you add the deuterium here, and you add the other deuterium here. And that's that Sen addition. They're all kind of similar, honestly, on how they add on. Does that make sense?
Yeah.
Okay. So this is called OSO4 is oxidation. In oxidation, all it does is it adds 2 OHs Sen to one another. So Sen, once again, same side. So once again, stereospecific for this addition. So you got to look at the stereochemistry. Since it's on a wedge, the OHs have to be added on a dash. So then you're going to get something that looks like this as your final product. Does that make sense?
Yep.
Okay, same thing for this one. And then this is your only product, once again, because it's stereospecific. Now for this one, same thing. It's going to add 2 oxygen or OHs Sen to one another. But since there's no stereochemistry present, it would also have an enantiomer. Is there any questions pertaining to oxidation?
I don't know about the rest of them, but I think I'm good.
Okay. So yeah, they all kind of follow a similar pattern. You see the Sen additions, they're stereospecific, and then they add Sen, so both same side. The only thing is some have Markovnikov and anti-Markovnikov, and B2H6 is one of those weird ones. Hydroboronation, that's what it's called. It's one of those weird ones that has the anti-Markovnikov, meaning the hydrogen is going to go where it's less substituted. So there's that. So MCBA, this is an anti-addition, and I'll show you the mechanism of how this works. So in order to see what it adds, look at the solvent. MCPBA adds an OH, and then whatever the solvent is. So for this one, it would add an OME. Yeah, OME. My bad handwriting strikes again. So the mechanism, I'll draw it out for you guys real quick because this one I actually can show you the mechanism. It's not insanely long. That is the one good thing about Dr.Paull is he does not make you draw mechanisms out. Unless it's for homework, then yeah, you have to. But I don't think he ever made us draw the mechanisms out for additions, except for a couple of them, right? I'm trying to recall. Oh, no. So an oxygen attacks that alkene and it removes it, and then it attaches with 2 bonds. Then what happens is it leaves to form the more stable carbocation in order for the methyl to attack, the O methyl, whatever that's called, OMe to attack. So then it would form this. And also that would then, since the methyl attacked from the back side, that'd be put on a dash. So now then when that occurs, this attacks like that. However, it undergoes an Sn2 attack, meaning that's going to invert that stereochemistry. So now then your isopropyl would be put on a dash, and the OMe that attacks would be on a wedge. And then this would be turned into OH, because then it would grab the H actually from right here. But I didn't show that in the mechanism. And this would actually be your final product. And then once again, it would also have an enantiomer, because anti-additions are not stereo specific. So you guys kind of see how MCBA works. The solution is what attacks that more stable carbocation, the OH bonds with either two wedges, two dashes. And then when it breaks off, when the OMe attacks, it actually inverts that stereochemistry because it's an Sn2 reaction overall, which then causes the isopropyls stereochemistry to flip, and the OMe takes over whatever the isopropyl's original stereochemistry was. And then, of course, since it's not a syn addition, it's an anti-addition, it has an enantiomer, meaning it's just the opposite stereochemistry is also formed. So yeah, kind of complex, but need any help, let me know. So same thing for this one. RC3OH is the same as MPD, undergoes the same mechanism. So all that would happen here is just gonna label that so you guys understand. And then OET attacks. That would actually then attack at that more stable carbocation. And then of course, H. That is make sense? So same mechanism. Yeah. Same mechanism, same everything. Kind of complicated, I understand. Cl2, so this is the same, it's an anti-addition, so it follows that same property. These are actually I can show the anti-addition way more efficiently with these. So all that happens here is when the Cl attacks, like that, it forces that into a wedge stereochemistry position, because it's actually, it can attack from either side, because once again, it's going to form the enantiomer. So once it does that, this will leave. And then since it's Cl2, there's no solution. The other Cl would then come in and attack from the back side, which would then form that. And then one more of these additions. And these are just anti-addition of halogens, is what these are called. So anytime you see Br2, Cl2, I've never seen an iodine 2 or I2. I've only ever seen Cl2 and Br2. That's all Daniel ever gave us last semester. But if you do see it with an H2O on the bottom of the that's the solution. And instead of adding another Br, it then adds an OH. So the mechanism overall would be and then they would actually add an H2O, and then the hydrogen, of course, would go off, blah, 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 blah. But I'm just going to show it as an OH attacking. And that would actually then form that. And then this then take over because it does the backside attack OH. And that would then leave methyl to have the stereochemistry flipped. And then the BR looks like that. And then once again, plus the enantiomer. And yeah, that's anti-addition of halogens. Nothing too complicated. And I think the final thing, yeah, I just put one ozone in here because it's really easy. So you cut it in half and literally that'd be your final product. It literally just slices the alkenes in half. And if it's more complex, you label this. So then 1, 2, 3, 4, 5. So then you have 1, 2, 3, 4, 5. And then on this side, you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And that's how you check to make sure that it's correct, that you split it properly. But yeah, that's everything. I left out spectroscopy and NMR because I didn't see it on the syllabus. So does anyone have any questions or is everything good? I know it was a whole lot of information in a short time frame.
I'm all good.
Yeah, I'm all good. Thank you so much.
Yeah,
No
no
problem.
questions here. But fortunately, you'll be posting it up on your YouTube so we can go back and see it again.
Yes, I'm hoping to break 5 views.
Thank you, Roz.
No problem. You guys have a wonderful night. And
You too.
How do I you have to send me the recording.
Yeah, I think you just end it.
Okay, sounds good. Well, have a nice night, everyone.
All right, you too.